So, hi, welcome everybody to today's MCK meeting. We have again two very nice, interesting talks. Let's start as usual with the IPCEI-CIS Code of Conduct that you are all aware of. We also show that at the beginning of each presentation. And as we open that also up to the Neonefos Foundation, we also have the Neonefos Antitrust Policy Notice. Exactly. And yeah, we have two topics as said. One is confidential computing revisited, where Matthias will present his market analysis and trends. And later on, we also have then ORD, UMS, and knowledge graph from Yong. So with that, I hand over to you, Matthias.
Yeah, thank you, Jan, for the introduction. So good morning. So I'm Matthias Gries from Cyberus Technology. Let me first find the screen that I want to share. One moment. So I believe you can now see the starting slide of my presentation. Yeah, so as Jan pointed out, this will be about confidential computing. There are actually already quite a few papers out there on confidential computing, so that's why I call it here Revisited. We look a little bit more into the technology readiness, usability, maybe also on market projections, and so on and so forth. I'd like to point out why am I here. This actually happened under the ApeiroRA reference architecture umbrella from SAP. So it's actually also here a contribution to the European project. But before we go into technical details, let me briefly say who we are. So Cyberus, we started 9 years ago. You see a few icons here on the upper left of like prior experiences of some of the employees. So I'm, for instance, an ex-Intel guy. So my background is actually more CPU microarchitecture, research and development. And I know our CEO, Torlund Larsen, already since 19 years. You may know us here on the top right. We started in 2018 with visibility when it comes to the discovery of the meltdown and spectra vulnerabilities in the CPUs and also follow-on vulnerabilities. We do like Linux KVM for virtualization. So also quite some visibility was raised when we provided a KVM backend for VirtualBox. We are in a few products from Secunet, also with a prior product from us that was still based on a microkernel implementation. I mentioned before, we are actually active under the ApeiroRA reference architecture for SAP, where we provide the cloud hypervisor as a virtual machine monitor for the overall cloud stack. And you may have noticed that at the end of last year, we also got Einsatzerlaubnis, so a temporary approval for use of this cloud hypervisor in a special setup defined by the German BSI authority. And maybe last thing here on the lower right, we do like open source. So we were founding members of the Alaska and Neonefos foundations. I mentioned Cloud Hypervisor. We like the Rust programming language because some of the security flaws with memory subsystems are avoided. And our current activities are all around Linux KVM. And we also do automation, test automation, for instance, with NixOS, and also provide long-time support for NixOS in a different branch, in a different business unit. Okay, let's start. What is actually confidential computing? So the kind of definition that I want to use here for this talk is from the Confidential Computing Consortium, CCC. So first of all, confidential computing means that it protects data in use. So it's complementary to data in motion protection in the network or data at rest protection in storage. So it's another piece in order to make your whole system confidential. For this to work, you want to work in a trustworthy, secure environment. For that, confidential computing provides an attestation step such that you actually see some evidence that the whole system is in a genuine state that you expect it to be. The kind of protection that you get by this, by data in use protection, is that you're actually protected against the service provider. So you're protected against, let's say, a host, an administrator with privilege rights, and also a hypervisor, also against the hypervisor. The very fact that I mentioned the hypervisor points out already the last bullet item here. So for this analysis, we focus on techniques that are based on virtualization. So confidential computing is essentially an extension of existing virtualization technology. And we look at two flavors here for x86, one from Intel TDX, and the other one from AMD SEV SMP. So overall, on a top level, they provide similar functionality. On the lower level, they're actually quite different. Just to give you an idea of the complexity of the implementation and the very fact that the implementation at Intel and AMD is actually different, I'd like to point out maybe 4 underlying technologies. There would actually be more, but let's keep it to 4 technologies. So first of all, the first thing that both technologies provide is memory encryption. And this is done individually for each virtual machine. So a different encryption key is used for each individual virtual machine to make it a confidential virtual machine. In order to provide this kind of functionality and maybe shift some functionality that was traditionally implemented in a hypervisor that you no longer trust to software modules that are now provided by the CPU vendors. The CPU vendors introduced new CPU modes to protect this special piece of software. So on the upper right, you see a block diagram using Intel TDX as an example. In blue, you see the TDX module. So that's a software piece that comes from Intel, but that runs in a special operating mode of the CPU that's called secure arbitration mode. It's independent of the address space of your virtual machine. At Intel, this is called a trust domain. So this green block TD, that's your confidential virtual machine here. You see that the TDX module now here has a kind of coordination functionality here and capability in order to instantiate and operate your trust domain. AMD does similar things, introduces new privilege levels, provides a secure VM service module, and so on and so forth. They actually also integrate a secure processor, so that's a system on chip that's independent but actually integrated in the CPU. So it's independent of the main CPU, and it's the kind of firmware here in the secure processor that does similar things compared to the Intel TDX module. The third technology that I mention here, attestation. I mentioned it before. You want to see some evidence that actually your trusted compute base is in a state that you expect. So the TDX module is quite vital. So you have to trust this module, and it's part of your TCB. So you want to see evidence that this has not been tampered with, for instance. And there's this attestation step on the lower right. Again, I use Intel here as an example. So you see here actually a flow chart, roughly speaking, where your guest system actually interacts with the CPU. So to ask the CPU to do measurements, these measurements are then handed over to a quoting enclave that runs on the host to convert this into a report that's actually signed. And this then can be given to an external verification entity that can check if, let's say, version numbers or hashes are the ones that you expect. You compare this against a golden model, and then you can define an attestation policy. So for instance, if, let's say, your BIOS is aged, maybe it's 3 months old, and there's actually a newer version available, you do not start the guest system. And the last technique that I mention here is a kind of double entry bookkeeping in order to make sure that the integrity of page table translations are kept. So there's actually an additional lookup step here where an additional lookup table makes sure that a private page can only be mapped to one virtual machine. So it's not possible that the host, so if the host tries to share one private page of one VM with a different VM, this lookup step should actually recognize this and forbid this. Now that I've explained what we define as confidential computing, maybe I should start with the motivation. Why should you use it, or why should you at least consider it and analyze it? Of course, there are quite a few reports out there that look at cybersecurity risks. And of course, these risks are increasing. Of course, your whole business could be at risk. And that's why there are already market projections that use the term confidential computing and that are quite optimistic. Of course, these projections can only look at a history of maybe only a couple of years in order to do these projections. That's also why market projections actually vary from at least 25% annual growth rate to more than 50% annual growth rate. But in general, the takeaway message here probably would be that 10 years from now, these companies see the potential that the confidential computing market could actually become bigger than more traditional markets like high-performance computing. So it could be a significant piece of the overall market for IT computing. And maybe another example that I wanted to point out here is by the company Gartner. So in the first figure from 2024, middle of 2024, you see the typical hype cycle from Gartner. I have to say, normally these figures are only visible when you pay for the report. This figure actually leaked on LinkedIn, so it was shared by several companies. So let me re-emphasize, of course, there's a copyright by Gartner. And the thing that I wanted to point out in 2024, Gartner saw confidential computing still at the beginning of this hype cycle. Yeah, it means at that time they thought it would still take maybe 5 to 10 years to reach the stable plateau at the end of the hype cycle where this technology is actually mature. Only 15 months later, in Gartner's top 10 strategic technology trends document, you see the figure here on the far right, and that's a public document. You now suddenly see that confidential computing is actually included in the top 10, and the period for reaching impact reduced to 1 to 3 years. So you also see here an increased sense of urgency that this technology becomes important. And you also see here this significant quote that a significant fraction of currently untrusted infrastructure will be protected by confidential computing 3 years from now. So that should at least be an indication that you perhaps should at least follow the trends here, what's happening in this space. And this brings me to the report. Why did we do this analysis? So we saw, on the one hand, we saw this complexity of the technology. I pointed out 4 underlying main principles that are implemented in CPUs. We also, of course, got early assessments from our network, from our partners, and we essentially got mixed results. Yeah? Some like the technology, some tried out maybe first proof of concepts, maybe were disappointed in the first step, and we also have partners that are essentially completely against it. Yeah? So we figured out, so maybe we should collect this information in a systematic way. And it turned out that when we started this, we also got SAP through the ApeiroRA reference architecture interested. So I'd like to thank Michael Schmidt. I also saw him here on the distribution list. I don't know if he's dialed in. So he supported this analysis from the very beginning. And also our CEO, Torlund Larsen, was very active to actually organize all these different meetings. Yeah, you see here an overview of the kind of interviews that we had. So we tried to really cover quite a spectrum of different sectors. So you see service providers, you see OS developers. We have both CPU vendors that we interviewed. We have companies that provide secure products, yeah, like Giesecke & Devrient, Rohde & Schwarz. We also looked at quite new companies that implement additional productivity layers based on confidential computing, like edgeless, enclave, Scontain. We had research organizations. We also tried to get some feedback from our accreditation process with the BSE, and so on and so forth. So eventually, I think we were also surprised. We ended up with quite some material. So this report, this is publicly available on the HAL Open Science Archive since March. So we submitted it in February. So more than 70 pages, 150 references, since apart from the interviews, of course, we also did a literature research. We looked at specifications, web pages, and so on and so forth. So let's now look at some of the highlights. Yeah, obviously, there's not enough time to go over 70 pages. So, but maybe to give you an idea of what you can find in this report. The first thing here probably does not sound that exciting. So why do I talk about regulation, standards, and consortia? So we asked our partners, what are the kind of standards or consortia regulations you can think of that perhaps over time could motivate you to use confidential computing? And the surprising fact is that we actually ended up with more than 30 items here. So on this slide, I only highlight a few to maybe show you different categories. So on the one hand, you can use confidential computing as a mitigation against existing regulations. So you can use confidential computing such that the US Cloud Act, where the US government could actually access data of a data center somewhere in Europe if the operator is actually a US company or has significant business in the US. Now you could use confidential computing as a means that this is essentially not possible because also your data in use is protected. Or you could use it whenever you process personal information. So whenever you do whenever you have an argument with a lawyer, yeah, how do you comply to GDPR? You have an additional piece here where you can say, also from a technology perspective, we use a technology that prevents data leakage to appear. It would not be enough to fulfill GDPR, but it could be an important step in this argument. Then there are other regulations and standards where data in use protection is actually already required. So one example is the Gematik here in Germany for healthcare, where data in use is requested. It could, of course, also mean that in a call for tender, you could also reply, let's say, with full homomorphic encryption. But for general use cases, actually, confidential computing is usually the common choice. It's only feasible in those kinds of setups. Or there's DORA in the financial sector, and here in Germany, we saw recently in January that the BSI, for instance, released this Leitfaden, so this general guidance on cloud computing or using cloud computing for confidential documents. And also there, they actually define different categories, and there's like one subcategory for public cloud computing where data in use protection would be recommended. You also have consortia as the last category here that are quite active to promote the technology. So there's this confidential compute consortium where I already used the definition of the technology at the very beginning. And depending on how you augment confidential computing, maybe you also use, for instance, a trusted platform module, a TPM, in order to save measurements, for instance. And then, of course, you rely on standards from the trusted computing group that has now been active for several decades already. So this overview of regulations, maybe another reason for compliance to use confidential computing is covered in the report. Now, let's look maybe at some more technical aspects. The example that I mentioned here is you as a user. If you want to use confidential computing, and let's say at this very moment, you want to use it as at an US hyperscaler, what are actually the kind of drawbacks that you have to deal with? In the report, there's also a complementary section that does a similar comparison for service providers. Here in this talk, I will only talk about the viewpoint of a general user. Yeah, so you as a general user, you want to use confidential computing, you buy it as a US hyperscaler. First of all, you will recognize that often it's actually a little bit more expensive. So you pay an additional fee, usually in the order of 5 to 10%. Unfortunately, the workloads that you run also become a little bit slower. So when it comes to compute and memory phases of your confidential virtual machine, the drawback, the slowdown is only in the order of a few %. But academic studies 1 or 2 years ago were, of course, quite vivid, quite visible, to show that whenever it comes to I/O traffic, so to network and disk storage, the performance penalty can be significantly higher. However, I have to tell you, this is not surprising, because remember, in your confidential virtual machine is protected. So when you now use the network or when you use storage, it means that actually this kind of traffic goes beyond your trust boundary. So your peripheral is no longer able to do a memory transfer into your virtual machine. So network traffic, disk traffic always has to go through an additional bounce buffer, and that's where this penalty comes from. So you have to be aware of this. And maybe you want to, I don't know, change the way your workload is implemented if this overhead actually becomes too high. You will also notice here the third bullet item, whenever confidential computing is offered to you, very likely the functionality is reduced compared to normal cloud offerings. So for instance, snapshots of your VM or monitoring information of your VM may no longer be available. I mean, that's clear. That's also must be true by design, because you no longer trust the administrator and the service provider by using confidential computing. You can re-enable this by introducing services into the guest. So you have to admit additional services into your guest, and by this you increase your trusted compute base. And with additional services, you can then allow the service provider to get monitoring information of the guest, for instance. Of course, you as a user, you want to make sure that the TCB is in a genuine state. So you want to use attestation. At this very moment, it's quite cumbersome. So rather low-level information that you have to deal with to really make sure what's happening. So you would have to look at all the source code. You would have to reverse engineer how reference values are being generated, like hash values, for instance. You have to be aware of all these things. That's why service providers also often offer their own attestation services, which somehow contradicts confidential computing. Yeah? So on the one hand, you want to get rid of the service provider. You don't trust the service provider, but for attestation, you may have to trust the service provider again. So there have been also nice papers about this state of attestation, how this can be improved. You found 2 or 3 very recent references in the report. But to also say something positive, yeah. So what about reusing software that you already have? So application code usually does not have to be changed. Sometimes maybe it has to be recompiled, because in your confidential virtual machine, at this very moment, you need a very recent operating system, so a very recent Linux kernel, since your guest must be enlightened. It must be aware of the very fact that underneath there's a confidential computing enabled host, because only then certain hypercalls are only possible, for instance, in order to trigger attestation. So there might be corner cases where still the source code of your application must be available in order to recompile it. But there are actually now also companies active in this area. So we call this lift and shift, where these steps can actually be automated. So it's a straightforward procedure for you to actually use confidential computing, even with legacy applications. Good. So what is confidential computing being used for? So there are, of course, case studies that are being published, particularly by the CPU vendors. I've pointed out here 4 different categories. So the first category is actually a traditional cost argument. Yeah, just like cloud computing, you now have a better version of cloud computing. Yeah, you can argue, or particularly hyperscaler will argue, please come to us, yeah, bring all your workloads to us. It's like cloud computing, but now at a similar security level as a private on-prem instance. Yeah, because with confidential computing, we as a service provider, we no longer have any access to your virtual machine. Then maybe a very different orthogonal line of argumentation. besides cloud computing that I also wanted to point out would be improving defense in depth strategy. For instance, for embedded systems, maybe a system that's used at the edge somewhere, but that could be tampered with. So maybe it's at some public place. So with confidential computing, you essentially want to make sure that reverse engineering of a system that's running becomes more complicated, becomes harder in the future. Then the third bullet item is actually a very vivid area where many companies try to put additional service into the marketplace based on confidential computing. So here we have multi-party analysis or multi-party computing. So for instance, you can use attestation in order to assure a data owner that the data is only used with an algorithm in a very well-defined environment. Yeah, so this environment, the processing part could be attested, and then you know, okay, only this particular algorithm is used with my data. Or you could for instance, track the provenance of the data with confidential computing. So then there are like clean analysis spaces defined that are enabled by confidential computing, and the data that's being processed is of course protected by encryption implemented by confidential computing. And of course, obviously, everyone likes AI. So also here we have use cases so you can actually protect all phases of AI. You can protect the training part. So you can protect the model, you can attest and log the provenance of the data that's being used for training the model. Or when you have a model already, when you use it for inference, you want to protect the model that it's not being stolen with confidential computing, but you also want to protect the input data and the responses of the model that are provided by the user. So also confidential computing is a good technology here because you know AI models, the best ones are pretty massive, so even pretty big. So even if you wanted to use an open weights model, it might be too big now that you can host it on your own. So you want to host it in the cloud, and you can now protect the setup with confidential computing so that your input and output prompt information remains private. Of course, an AI model is a digital asset. So another way to look at this would be that you actually protect a digital asset. So the last bullet item here, however, is usually used, this term is usually used by finance, by the finance industry, for instance, or by ID wallets. So that you emphasize that this is, of course, critical, perhaps personal information that you have to protect, where confidential computing, again, is an additional layer of protection such that the data stays confidential. Now, here with ApeiroRA reference architecture and Neonephos, of course, we like open source projects. So also in the report, you will see quite a few open source projects mentioned. I selected a few here just to give you maybe an overview of the breadth of solutions that are out there. So I mentioned lift and shift, whenever you want to use your former application now with confidential computing. So there are commercial solutions, but there are actually also open source solutions. So there's a project called Confidential Containers, where actually individual Kubernetes pods, so container pods, can be moved into confidential virtual machines, such that you get an extra application level separation of the workloads, an extra level of protection. I mentioned that attestation at this very moment, when you have to deal with attestation, it's pretty low level, probably quite confusing to start with. That's why there are actually quite a few projects active here. I mentioned only 3. So a trustee, for instance, would be an open source framework as part of confidential containers, where you actually get an attestation kind of thing for each container pod, so on an application level, not on a whole blob, but actually on an individual application level, you get an attestation that this is the kind of workload, the kind of container pod that you expect. Virti, as another example, this is usually a good starting point for everything on AMD, as an example. So when you look at the documentation at hyperscalers, they often rely on Virti, and it's a project of the CCC consortium. And the last example here, Verizon, was actually initially developed by ARM and also contributed to the Confidential Computing Consortium. There are also activities along the lines of a paravisor layer. So I mentioned before that at this very moment, your guest operating system must be enlightened. It must be aware of being run on a confidential computing enabled host. And maybe to reduce this burden, of course, you could use a paravisor layer so that this paravisor actually does some of this transformation for maybe a legacy VM. This is work in progress. So OpenVMM, this is actually a project pushed by Azure. So this is more towards an implementation on AMD. Also, the second project here, Coconut, the Coconut Secure VM Service Module, initially started with AMD on AMD, but they recently also opened up this functionality to the Intel technology. And towards the end of last year, actually all major Linux distributions announced support for confidential computing, not only in a virtual machine, not only on a guest, but also on a host, based on Linux KVM, QEMU, and libvirt. So that's a typical combination that's offered in Linux distributions. So
Matthias,
you may now, yeah.
Let me use the pause that you made. So 5 minutes left for you. So thanks.
Okay. I'm fine. Okay, so you may also wondering what's the overall landscape. I mentioned Linux KVM. So starting with kernel 6.16, you no longer have to patch your KVM. So it actually comes with the mainline implementation. It should work out of the box. We at Cyberus, we are active on Cloud Hypervisor. The AMD technology, the initial support recently started 1 month ago. Unfortunately for Intel TDX, it's a little bit rotted. This is actually mentioned in the ticket there. So at this very moment, Intel TDX would not work. So when you use confidential computing at hyperscalers, you will notice that it's often not the newest CPU generation. It's often 1 or 2 generations behind. But this actually changed a little bit within the last 2 to 3 months. So maybe there's also a higher sense of urgency. In Europe, however, it's very difficult to find those kinds of services at this very moment. So on public offerings, at this very moment, you probably have to do it on bare metal. There's an appendix in the report where I give a brief overview of companies that provide additional services implemented with confidential computing. So we have players in Europe like Edgeless, Contain, Enclave. These are all companies in Germany, for instance, and in the US, Arjuna, Opac, Fortanix are probably quite visible. So now let's wrap up the interviews. That's the last topic of my talk. So we interviewed more than 40 different individuals, and I put them in 3 categories. So we have the optimists. US hyperscalers would be in this category that tell you in a few years from now, this will be the default mode of operation. Everyone will use it. You will be left behind if you don't adapt this technology. Yeah? And of course, CPU vendors are also in this category. However, most of the interviews were actually eventually in this realist category. So they understand the pros and cons of the technology. I mentioned a few already. People realize that maybe you will need this technology for compliance in the future. It's better than nothing. You have to start somewhere. So you should use the time now to actually build up knowledge in your company, either to use it or to implement it in future products, such that you're not surprised. And a realist usually thinks that this technology is at a medium technology readiness level. So they will probably monitor it for another 1 or 2 generations and then adapt it eventually for a product. And of course, we also have pessimists or opponents that say it's too complex, it's easy to break, it's maybe the wrong approach because attestation cannot prevent bugs to appear. Attestation only acknowledges a version of your software, but of course your software could be very buggy. So a better approach would be to really reduce the complexity of your trusted computing base. And the service provider should actually be part of the TCB. So they think this is actually the wrong approach to exclude the service provider from the TCB. And you may have noticed that, the US government now has a stake in Intel. So that's maybe yet another reason why you don't want to rely on US technology anymore. So to wrap up, hopefully, at least here with this overview, you should have noticed that confidential computing is not a magical solution. It's a piece of the puzzle. You still have to combine it with data at rest and data in motion protection to eventually reach confidentiality. So for instance, that also means that there are still side channels. Side channels are not prevented. So you still have to harden your guest with the best known methods against side channels. It's work in progress. It's still a very recent technology. It was only introduced 3 years ago, roughly speaking. It now has become part of the Linux mainline kernel, so that's good. And maybe in the future we will see standards around attestation, maybe even from Europe. And this maybe also gives us maybe a perspective that at least attestation services midterm could also be offered here in Europe from a trusted entity. Of course, we still lack a European CPU and we don't have memory and we don't have storage. That's bad. So what's the outcome for Cyberus? So we are also in the realist category. And of course, we currently try to position maybe more a research and development project, not like a production level kind of thing. Also under the ApeiroRA reference architecture umbrella to, for instance, re-enable the Intel TDX implementation in Cloud Hypervisor. Okay, thank you. That's all.
Thanks, Matthias. Very interesting. Do we have maybe one question? Okay, so Matthias, I guess I can say if there are questions coming up later on, they can contact you through your email. And thanks a lot for your presentation. Would you be willing to send over the presentation afterwards to me, please?
Yes,
so that
I can do
include
that.
them. Yeah. Good.
No problem. Okay, so thanks for having me.
Thanks a lot, Matthias. And with that, handing over to Yong.
Yeah, hello. I hope you can see me now. Wonderful. I got a new laptop, that's why I'm asking. So please, I will try to share my screen and so that you can see everything what I have to share. And I guess you see now my screen. Wonderful. Yeah, please let this sink in. This is my topic for today, for the next 30 to 40 minutes. I'm not sure at this moment if you had the chance to hear something about the topics I will clarify with you. And I'm not sure if this has been shared to a non-SAP audience. So that's why I'm pretty excited and I'm also interested in your feedback here. So my topic is how ORD, Open Resource Discovery, UMS, Unified Metadata Service, and the Knowledge Graph make metadata the backbone of open cloud edge ecosystems. Just in case you don't know where we are coming from, we are in this layered data fabric. Yeah. And we have the three topics: Open Resource Discovery, Unified Metadata Service, and Knowledge Graph. Maybe you are now wondering, why is it the case? What is it for? What is the value? What is the reason? Why do we have this at all? And please join me this journey and I will try to explain that. So the challenge for Data Fabric. And I wanted to start with this slide. Because I think in that case, I can also a little bit introduce myself. My name is Yong Sok Song. I'm with SAP since 18 years. I started as an IT consultant, was working for several customers, and we had always this problem that when we got to a new customer, we had a certain IT landscape. And when the customer wanted to have some kind of a transition to a new architecture, and we needed to support him, then what we first have done was always to paint something like an IT landscape. And this is not something, an actual customer landscape. This is AI generated. But this gives you a glimpse on what do we actually have, right? And when you look in our current landscapes, be it SAP, be it integrator, be it the customer, be it somewhere else, I think every time we have to deal with many systems, many interfaces. Not only the technical perspective is covered. I mean, as an IT architecture consultant, we were only focusing at that time on technical things, but nowadays, and this was also true in former times, we need to show that something like high availability is provided from that landscape, or certain customer processes are supported. And with this, I mean, alone the technical interfaces, yeah, when we have this N systems, and when we would like to connect these technically with interfaces, then we have this complex or this square formula where we have this N times N possible connections. And yeah, I don't know if you can see that there we have here around, I don't know, 100 systems. Then we would have 100 times 100, and we are talking about 10,000 possible connections. And these are alone the technical connections. And when you now think about non-technical connections between the systems, we are talking about even more. And this is a foundational problem I want to discuss with you in the next slides. And I hope you can go with me and understand where we are going to, because this is maybe not so easy to understand from the first start. So, as I have shown you, yeah, this technical landscape, we are talking about technical interfaces, but we are also talking about non-technical interfaces. Yeah, we have characteristics of an IT landscape. And I think these are some examples: operations, monitoring, incident management, security. Every topic have spans a net throughout these systems, and you as an IT operator or an admin or service integrator, you have to deal with these, yeah, because a landscape has certain key aspects to fulfill. And at SAP, this high availability, I think this is not a huge secret. This is one of our most highly desired key metrics to fulfill. And when we would have something like this request from our management, yeah, show me every customer-facing service, yeah, that depends on the network feature Z and security requirement X and has an SLA above 99%. Yeah, what would you do today? Yeah, you have to walk this map yourself. Every service exposes itself differently. Yeah, every concern behaves differently per service. Yeah, and every consumer integrates N times once per customer, and every provider exposes itself N times to something else. Yeah, the number of connections grows with the product, and not the sum. So that is a N times N problem in one picture, and maybe even more. And every one of those connections in a place where things deprecate, drift, and silently break. Yeah, we know that because we have these catalogs also in our landscapes. And when you are not maintaining them, when you are not getting the current actual data from these components, then it gets old. Like these IT landscape pictures we have drawn in the past. And this is a challenge, right? The mess on the slide isn't a failure of architecture. Yeah, the architecture is fine. It's a failure of metadata. That's exactly what the rest of this talk is about. ORD, Open Resource Discovery, lets every box describe itself. uniformly. UMS aggregates what the rest, UMS aggregates those descriptions, and the knowledge graph turns them into type relationships, and an agent can traverse on that. Same landscape, but self-describing, queryable for everyone. Understanding the problem. Everything is like a black box. And I think the more information we get, it's sometimes even harder to get through the jungle. That is just a statement. Maybe we need to revise it. So this n times n topic. This one shows you why this happens. Look at the 4 columns. Each is a different domain of metadata, each with its own discovery protocol and its own catalog. APIs and events, Open API, OData, Async API. Each grade on its own, each with its own portal registry and conventions. Then we have AI tooling, MCP, A2A, agent cards, a space barely 2 years old that has already invented its own catalogs. Data, data products, data sharing, a different community, different tooling, different format, a data engineer and an API engineer at the same company have no shared vocabulary for what their systems expose. Business, taxonomies, business objects, processes, usually in a glossary or an enterprise architecture tool, completely disconnected from the technical specs. 4 columns, 4 catalogs. Not 2 of them share an identifier, an ownership model, a visibility model, or a life cycle. A developer building a portal wires up 4 catalogs. An agent planning a multi-step task speaks 4 different discovery dialects. Governance is asking who owns it, and we need to query 4 systems. The protocols themselves are definitely not the problem. They are each great at what they do, but the problem is there's no shared layer above them. And that layer is what we want to provide. The same picture as before, same 4 columns, but notice what changed at the bottom. Instead of 4 silos, every column now points to one discovery protocol, into one metadata catalog. The sphere is ORD, and this picture is the whole thesis of the talk. I want to be precise here, and sure about what we are trying to claim and what we are not trying to claim. ORD does not replace Open API, MCP, data sharing, or your business taxonomy. Those stay exactly where they are. Open API describes the shape of REST calls. Async API describes an event. MCP cards describe a tool. Each is a contract for one specific thing. But what ORD adds is an envelope around them, a stable identity, an owner, a visibility level, a lifecycle stage, a policy level. The relationships to other resources, the native specs, stay the source of truth for the technical contract. ORD answers the questions: who owns it? Who can see it? Where does it sit in the landscape? How it relates to everything else? Once, in one shape, or one well-known endpoint per provider. That's what collapses 4 silos into one backbone. The payoff on the consumer side. A developer no longer learns 4 catalogs. An agent no longer speaks 4 discovery dialects. Governance no longer queries 4 systems. One protocol, one catalog. That is the backbone, everything else. In this talk, UMS, the graph, sits on top of it. Now, we have the data. We are trying to build the ecosystem above it. So, but first we need to dive in how we are doing that. This is this ORD. the open resource discovery. This hexagon in the middle is one service, anything, a microservice, a SaaS product, an ABAP system, an agent. ORD's job is to let that one thing describe itself in a uniform machine-readable way. One application equals one document. On the left, you see taxonomy, how the application organizes its own metadata, packages, entity types. For example, I don't know, and entity types are, for example, the business objects, supplier, purchase order, stable namespace names that let a graph connect things across services. Data products, maybe you have heard this the first time, are first-class consumable datasets with an owner and an SLA. Integration dependencies declare what this application needs from outside to work. Capabilities are open-ended, slot for typed features that aren't a classic API, an MCP server, an agent card, and so on. And here's the most important sentence on this slide. ORD doesn't replace open API, async API, EDMX, MCP cards, or agent cards. ORD just points to them. Each contract stays in its native spec. ORD wraps them with the metadata they don't carry: identity, ownership, visibility, lifecycle, and policy. The small circle on the right, this is the ORD provider API. So this is how all of this gets served. A one well-known endpoint per provider, just a small HTTP server. No vendor-specific registry, no point-to-point integration. ORD is the wrapper that turns a service into something the rest of the ecosystem can find, trust and build on, without forcing every provider onto the same underlying spec. If you want more information, this open resource discovery is open sourced. You can go through it and also build today your first own ORD document. So let me wrap this up. So what is important for when it comes to ORD? ORD lets you build a unified, well-connected catalog for everything integration related, APIs, events, data products, and so on. 2, discovery is fully automated in real time. The provider publishes, the crawler picks up the change, the catalog stops being a snapshot. Somebody updates by hand and becomes a live projection of the running landscape. No more API drift. 3, you see the actual system landscape, not just a static product offering. Same protocol describes what is theoretically available and what is concretely deployed, in which tenant, at which lifecycle stage, with which visibility, and so on. That's what governance, AI agent, and tenant-aware tools need. 4, ORD is extensible and complementary. Open API stays, async API stays, season stays. ORD points at them and adds the layer above. That's a property that makes adoption realistic. We are not asking teams to throw away their specs. 5, the one that matters most: share the discovery protocol, share the metadata infrastructure, share the governance. Don't rebuild it for every new technology. The cost of integrating the next wave, agents this year, whatever comes next, should be writing a new resource type in ORD, not standing up another catalog and another identity model. So one backbone, many resource types, that is ORD. Now let's go to the next step. Unified metadata service, from many ORD endpoints to one query surface. So why do we need UMS at all? When ORD already federates the truth, why UMS? So with UMS, you register an ORD provider in one place: the URL, the access strategy, credentials, the tenant scope. and that's it. UMS schedules the crawl, triggers it on demand, surfaces validation failures and errors in one place, and does the same job for every consumer downstream. Catalogs, knowledge graph, agents, governance models, or tools. None of them crawls providers anymore. Yeah, they all query UMS. So without UMS, ORD endpoints stay federated. Yeah, and maybe that's good for ownership, but bad for consumers. Every provider runs its own well-known endpoint, and so every consumer that wants the metadata has to do the same work over and over again. Register each provider, authenticate to it, schedule the crawl, run the crawl, handle the errors, validate what comes back, and store the results. And the n times n integration problem, what we have talked before, we said ORD solves at the protocol layer, comes back at the operational layer as n times n crawling. And there is no shared place to validate the documents, no shared place to track lifecycle, no shared place to audit who saw what. So the shift in one sentence, the work of crawling and validating ORDs endpoints moves out of every consumer and into one shared layer. ORD stays federated, their federation matters at the source of truth. UMS centralizes only what generally should be shared. How we manage ORD documents. 3 columns, 3 steps. First, provider registration, on the right-hand side. You give UMS the well-known URL, the access strategy, MTLS, or out, whatever the provider requires. And you bind the registration to a tenant and a visibility scope. One provider can expose several ORD documents. UMS tracks them all under that single registration. Second, ingestion and normalization. UMS crawls on a schedule and on demand. Every document is validated against the ORD specification. Invalid documents are rejected, never silently stored. Then identities are resolved across providers. Lifecycle, version, visibility are kept as first-class fields, not hidden inside the document. Third, storage and access. Every resource API, event, data product, entity types, capabilities become a typed record. Visibility and authorization are enforced at the query layer, not buried in the JSON. So the same store can serve a public catalog and an internal knowledge graph from one source of truth. Register, ingest, store. That is what UMS does to ORD. To summarize, this is the bridge between UMS and the knowledge graph. But the knowledge graph does not crawl the providers. It reads just only the UMS, just to be precise. The single design choice changes what the graph has to worry about. UMS deals with the metadata that is already validated against the ORD specification, already identity resolved across providers, already lifecycle and visibility aware, and already tenant scoped. 4 properties, all guaranteed before the graph sees a single record, which means the graph does not have to reinvent any of them. It can focus on the things only a graph can do, turning typed records into typed nodes and typed edges, layering an ontology on top, and answering multi-hop reasoning questions across providers. If you want one sentence to take away from this whole section, it is the bottom of the slide. ORD federates the truth, UMS makes it queryable, the knowledge graph makes it reasoning ready. 3 layers, 3 jobs, no duplicate work. Now let's come to the fun part. Knowledge graph from aggregated metadata to semantic reasoning. This is also one of the main questions we get. And just for your information, we are doing that within SAP as well. Yeah, this is a very important topic. This is the foundation slide for the knowledge graph section. Just maybe you don't know what knowledge graphs are. The data model. A knowledge graph is not a table, right? It is a network of typed nodes and typed edges. Every node represents a thing, a service, an API, an event, a lifecycle. And every edge represents a relationship between things with a name, whatever. But both the nodes and the edges carry properties, identity, ownership, lifecycle, and so on. So you are not just storing what exists, you are storing how things relate, yeah? What they mean, where the information came from. That is a structural difference between a graph and a row in a database. Now, why does this matter for AI? Agents do not need more records. Yeah? They need meaning and connections. An agent looking at a flat list of APIs has no idea which ones are related, which ones supersedes which one to call next. A graph turns that scattered metadata into a meaningful book the agent can traverse, filter, and reason over. Without it, every agent has to hard-code the knowledge of every service it touches, which does not scale and breaks the moment the landscape changes. Now look at the picture at the bottom. Yeah? This is just a small example, yeah? Of one IT component maybe. This is an example implementation. A service, 5 edges going out, each one a typed relationship to another node. Yeah? The service exposes APIs, publishes events, has a lifecycle and a version, and is observed by monitoring. It's secured by a security profile, 5 typed relationships, 5 typed nodes. And that is already enough to answer questions you cannot answer from a flat catalog. Which APIs does this service expose? Which version is this service in? Is it being monitored? Who cares, or who secures it? And each of those is one-step traversal. And as soon as you connect a second service into the same graph, you can start asking cross-service questions, which is exactly what the next slide is about. So on the left, we get the ORDs via OMS. Yeah? This is a primary stream. And you can see in the picture hexagons of application services with their APIs, events, data products, entity types, and so on. UMS hands all of that to the graph, already typed and validated and identity resolved across providers. Ownership, visibility, lifecycle, and policy levels arrive as first-class fields. Integration dependencies arrive as explicit edges between providers, consumers, and resources. The graph does not have to do any of that work itself. On the other side, complementary semantic sources. Yeah, so that is where also another side, another dimension comes into the game. ORD gives the graph structure. These gives it depths, shared ontologies and standards, yeah? Domain models, taxonomies, supply common vocabulary, so concepts in different services can be linked. Yeah? Overlays, let third parties enrich metadata they do not own, yeah? Without forking the provider's document. So 2 streams, 1 graph. ORD provides the structured backbone, semantics and runtime signals fill it in. And that is what makes the queries on this next slide possible. This is where everything we build pays off. The question is on the left on the picture. The service owner walks up to the system and says, an IT component is going to be deprecated. Show me the impacted services. That's a sentence anyone in operations has had ever to answer manually in a spreadsheet or with a week of email. Now it gets a single prompt. The agent in the middle takes the prompt and does what an agent should do in this architecture. It doesn't call 10 APIs and glue the answers somehow together. It walks the graph, same graph we built 2 slides ago. The component sits in the center, surrounded by typed edges to its APIs, events, lifecycle, and monitoring, security. And every other component that declared a dependency on it. The agent walks those edges and answers 3 questions in one query. The API service, API surface, consumers, and lifecycle. 3 questions, 1 traversal. No archaeology, no spreadsheet, no week of email. Without the graph, every deprecation is archaeology. With the graph, it's a traversal. And the same architecture answers availability questions, ownership questions, readiness questions. Anything depends on knowing on how things connect across federated landscapes. And when the next time some IT executive asked on how AI will help us run a complex IT landscape, the answer could be it requires a backbone, like I have proposed here. So we talked about ORD and what UMS organizes. And this is the last slide, and it's about why we go on further with the knowledge graph. The simplest way is to make the point is to look at what the world looks like without one. Today, a service gets deprecated. Every impact analysis is an archaeology. Someone digs through wikis, Slack threads, owner lists, spreadsheets, whatever, and every team produces their own view in their own format. Metadata exists everywhere, but it lives as scattered records, not as a connected model. With a knowledge graph, the same questions become traversals. And deprecation impact is one query, just as an example. Not a quarter of cross-team emails. Agents, for example, they reason over a shared semantic model that we maintain once. Impact analysis collapses from n teams and n spreadsheets to a single traversal, and metadata stops to be records. It becomes typed nodes and typed edges. Exactly the substrate AI agents need to ground their answers without hallucinating. And this is also why the ApeiroRA project's positioning matters. The knowledge graph is the layer that grounds agentic AI in real enterprise context. It takes the metadata, UMS aggregates it, layers semantics on top, and let domain experts extend the model. OID federates the truth, UMS makes it queryable, the knowledge graph makes it reasoning ready. Just as a remark at the end of this presentation, we are not doing this whole AI stuff. We are integrated in the end-to-end AI use cases, and we know that we need these semantics within the knowledge graph. Otherwise, the AI agents, the AI tools tend to hallucinate, and that is what we want to avoid with this backbone. But AI is not the only use case, right? So we are open for more use cases and more scenarios to come. So that's it, Jan.
Perfect. Thanks a lot, Young, for your presentation. It was very interesting as well for me to see everything in a more structured way. Was really good. Any questions coming up? And yeah, sorry, Jung, also that there are like only 9 people left. So we will share it on all the channels that we have. Yeah.
Okay.
And would you be willing to share the presentation, please, with me afterwards?
Yeah, I will do that.
Okay. Thanks a lot, colleagues. Have a good day. Bye-bye.
Bye-bye.
Thanks, same to you. Bye-bye.